There's this hidden logic that's running pretty much everything we do. It's in our phones, it's behind massive construction projects. There's this secret language of networks that's always at play. And today, we're going to learn how to speak it. Have you ever really stopped to think about it? We tap a button on a screen, and suddenly this incredibly complex series of events just happens perfectly. How on earth does your GPS know about that traffic jam 3 miles ahead? Or how does a project manager know the absolute rock bottom earliest state a giant project can possibly be finished? You know the feeling. You're running late, you type an address into your phone, and bam, it spits out the best route, and it's even recalculating on the fly. That's not magic. It's a really powerful set of rules working behind the scenes. Or think about building a house. It's just common sense, right? You can't paint the walls before the frame is up, and you can't put up the frame before the foundation is poured. Figuring out the true minimum time to get the whole thing done is all about understanding those dependencies. Well, the secret to both of these problems, and a whole lot more, is something called graph algorithms. It's basically a toolkit for making smart decisions inside of networks. And to really get a feel for how they work, we're going to roll up our sleeves and tackle 3 classic puzzles. Okay, let's dive into our first puzzle, project planning. Now, this is where it gets a little weird. You'd think the goal is always to find the shortest way to do something, right? But believe it or not, the key to finding the minimum time a project will take is actually to find the longest path. To figure this out, we first need to map out our project. We use something called a directed acyclic graph, or a DAG. Whoa, big words, right? But stick with me, it's actually super simple. All it means is that tasks flow in one direction, like our house example, and you can't have a situation where you get stuck in a loop, like needing to finish the painting to start the framing, which you need to finish the painting. It just wouldn't work. So let's just look at this simple plan as a graph. First, you pour the foundation. That takes 3 days. Once that's done, you can build the frame, which takes 5 days. Now, with the frame up, a couple of things can happen. You needed to install the plumbing, which is 4 days, and you also needed to finish the exterior, which is 2 days. And finally, you can also paint the interior once the frame's up, and that takes 3 days. So here's the absolute key takeaway. The project is not finished until the longest sequence of tasks that depend on each other is complete. Yeah, you can work on the exterior while the plumbing is getting installed, but neither one of them can even start until the frame is totally done. This longest chain of dependencies, that's what we call the critical path. And for our little project here, the critical path is foundation, then frame, then painting. So that's 3 days, plus 5 days, plus another 3, which gets us to 11 days. The plumbing path is also 11 days, but since no dependent path is longer, that's it. 11 days is the absolute fastest this project can get done. It's the longest path algorithm that gives us that magic number. Okay, let's move on to our next puzzle. We're going to switch gears from the longest path to one we're all a bit more familiar with, finding the shortest route. This is the engine behind every single GPS and mapping app you have ever used. To really get how your phone does this, the source material gives us this absolutely brilliant analogy. Just think of it like a fire spreading across a map. This is the beautiful idea behind Dijkstra's algorithm. It starts a fire right at your current location. Now, this fire spreads out in all directions, but, and this is the clever part, it travels faster along roads that are quicker, with less traffic or shorter distances. It always explores the closest unburnt spot first. That's a guarantee that the very first time the fire reaches your destination, it got there by taking the absolute shortest path possible. But, and this is a big but, Dijkstra's has one golden rule for it to work. All the costs have to be positive. Whether we're talking about time or distance or money, it has to be 0 or more. You can't have a road that takes negative 10 minutes to drive on. It just doesn't make any sense in this kind of model. But hang on, what if you could have a negative cost? Imagine a delivery route where taking a certain toll road actually gives you a fuel rebate. That's basically a negative cost, right? Dijkstra's algorithm would get totally confused by that. But don't worry, we've got another tool in our toolkit for exactly this scenario. And this is where the Bellman-Ford algorithm steps in. Now, it's a little bit slower than Dijkstra's, but it's way more robust. It can handle those tricky negative values. So think of it this way. For your everyday drive across town, Dijkstra's is your go-to. It's fast, it's efficient. But for some kind of complex logistics puzzle with rebates and rewards, Bellman-Ford is the tool for that job. All right, for our final puzzle, we're going to flip the script completely. We're not trying to find a path through a network that already exists. This time, our job is to design the network itself. We have to connect everything together for the absolute minimum possible cost. The answer to this puzzle is what's called a minimum cost spanning tree. Just picture this. You're in charge of laying down fiber optic cable to connect a bunch of cities. Or maybe you're building a power grid. You have to connect every single point. You want to use the least amount of cable or wire possible, and you've got to make sure there are no pointless, redundant loops. That's exactly what a minimum cost spanning tree does for you. And there are two main ways to build one. First, there's Prim's algorithm. This is like growing a crystal. You start at one point and you just greedily add the cheapest possible connection to expand your network outwards. Then there's Kruskal's algorithm, which is totally different. It's like building bridges between a bunch of islands. It looks at all the possible connections across the entire map, builds the cheapest ones first, no matter where they are, and slowly merges all these little separate clusters into one big connected network. In the end, they both get you to the same minimal cost. They just take a different approach to get there. So, after tackling those three puzzles, you've basically just acquired a powerful new toolkit for understanding the hidden logic of all kinds of networks. Let's put it all together. So really, it all just boils down to picking the right tool for the right job. Every puzzle we've walked through maps directly to a real-world problem and a very specific solution. If you need to figure out the bare minimum time for a project, you're looking for the longest path. If you need the fastest way to get from A to B, that's Dijkstra's or Bellman Ford. And if you need to build a network and connect everything for the lowest possible cost, you're building a minimum cost spanning tree with Prims or Kruskal's. It's all about knowing which question you're really trying to answer. These aren't just abstract ideas from a computer science class. They are the invisible rules that are constantly optimizing our travel, managing our most ambitious projects, and building the very digital and physical infrastructure we rely on every single day. So the real question is, now that you know the logic, what hidden networks are you going to start seeing all around you?